Okay. Okay.
Oh,
All right.
thank you. Thank you.
Okay. Thank you, Murugan. If the participants are able to hear me, oh, okay, they can all hear. Okay. Maybe let me see whether it is difficult on online to have interaction, but at least some of the interaction I must have so that I will know whether I am communicating correct material or not. Okay, fine. Now this is my contact mail ID. Okay, jebarajanna@gmail.com, and I still have the Anna University along with my name. So Jebaraj Anna, I made it. I made a Gmail ID. Okay. In case if you want to ask me anything, even after the course is over, yeah, I am available on this mail ID. I'll respond to you. But only thing, you have to make mention that you attended the Panimalar College FEM TTP. Okay. So that I will know what I would have delivered at that time, because I deliver to the industry people, it will be different type. So I must now know what is the information that you would have got it. Okay. All right, let's move on. So I'm now going to teach you if you are going to be a lecturer in the next semester, how you must teach FEM. And some of you may be sitting here because everybody is talking about FEM. Let me also go and see what is FEM, just as an onlooker. There may be some serious-minded people that they are working on FEM, they are guiding students on FEM, and they want to keep their material clean, recorded. I will ask you now, Murugan?
Yes, sir.
Okay. I will ask you to give me now, I'll give an assignment to these people.
Yes, sir.
Okay, everybody is going to open your chat box and give me a reply. You are here, one. I'm going to teach FEM. Then you type one. You are going to sit, you are sitting here because everybody is talking about FEM. I just want to listen what is it all about. Onlooker. Number two. And you are here more serious that I'm a researcher or I have my students working on projects. So I want to know a bit more about FEM. Number three, you belong to 1, 2, 3 category. In case if you are going to identify yourself as out of this, put as 4. Okay, 1, those of you who are going to teach FEM. Or you may be teaching FEM, it doesn't matter. You all belong to one. Second category, you are sitting here as an onlooker. And third category, you are a serious researcher or guide. Fourth category, none of the above. Please open your chat box and give your feedback. And I'll give you 2 minutes time for Murugan to give me the number for 1, number of 2, number of 3, number of 4. Is it clear?
Yes, sir. Yes, sir.
So Murugan, I'll give you 2 minutes. By the time whoever is responding, count the score of 1, how many, 2, how many, 3, how many, 4, how many. I know basically you're all college lecturers, okay? There is no gradation in that, but in that, you come under 1, 2, 3, 4. Murugan, chat box count பண்றீங்களா?
Yes, sir. I'm counting now.
சொல்லுங்க.
So there are more 3s, sir. I think 10 people 3. 8 people put 1.
1.
I think more or less equal now.
Okay. 2 and 4 nil. There is no onlookers. Everybody is serious. Series
Yes,
minded
sir.
people.
1 and 3 is coming.
1 and 3 are coming. Okay.
Many
Okay.
have put 1 and also 3. 1
Okay.
and 3.
Right. All right. Thank you very much. Thank you, Murugan. I
Yes, sir.
consider this group as a serious group. So I have to definitely meet your requirement that your seriousness is not to just while away the time. I give enough correct stuff so that you'll go at the end of this day, at the end of the course. It is good that I came to Panimalar and I got something to satisfy me. Okay, thank you. All right, if that be the case, let me take my next slide. I have asked the first question. Um, will somebody read it for me? The first question? Anybody? I think they have access to open the mic.
Yes, sir.
Malam.
They can
Okay.
unmute and speak.
Yeah, you can unmute and speak. Read the first one. I'll go with the known names. Is Mullakuri is there? She was my student. I can boldly ask her. Can you read the first question, Mullakuri? Read.
Yes, sir. Good morning, sir.
Read.
Why CAD, CAM, and CAE, CAPP, and CAX? Why?
Okay.
Why computer aided design and computer aided manufacturing and computer aided engineering?
Read. Read, man.
Sir, I read, sir.
No,
I want to
computer
give the
engineering.
answer. Yes, sir.
No, computer
Computer
design, computer
aided
engineering,
uh,
manufacturing, computer
process
design. It's better that we know computer process planning.
planning
And
and
what is the last
computer
one?
aided. X means multi in some other aspects.
Today, the desk can be filled with anything.
Yes, sir.
Desk can be filled with anything. There is computer aided inspection.
Okay, sir.
There is computer aided drafting. Okay. And that X can be today filled up with anything, everything. Every courses are now becoming computer aided. Okay. I told you when I did my engineering, I never had computer aided design, I never had computer aided manufacturing, I never had computer aided engineering, I never had computer, no. But today, all these subjects are there in our curriculum. In Anna University curriculum, all these subjects are there. Okay. And depends upon the specialization, metrology will have the inspection. Then vibrations guys will have the computer aided testing. Okay. And there are so many things. Computer aided X has come to replace everything. Okay. I asked the question why. We have two design courses, am I right? Design 1 and design 2. Or we call it a design of machine elements and design of transmission system. I think the name varies from university to university. Okay. Now, generally, semester 4 will be design 1, semester 5 will be design 2, and semester 6 will be computer aided design. After doing design 1 and design 2, where you teach them about design of machine elements and design of transmission system, everything, every joint, every motion, everything. Then sixth semester, they introduce a new subject called computer aided design. Is it because that your design 1 and design 2 is not enough, so you have to teach them computer aided design in the sixth semester? Then you do sixth semester computer aided design, in the seventh semester they say computer aided engineering, FEM. Why? After all, you make your design engineers. If design 1 and design 2 is not enough. Enough. I have an example that I learned only design 1 and design 2 in GCG Coimbatore. And I could do design of automotive, design of aircraft, design of spacecraft, design of atomic energy structures, anything. Your design 1, design 2 is knowledge enough, sir. Why they have added computer-aided design? It's a fancy. Because software industry is growing up everywhere, they saw computer. Okay, the company also add computer. Come on. Computer-aided design, computer manufacturing, computer, everything into it. Is it a fancy? Is there a real need for computer to come to help us? Isn't it that your knowledge as a design engineer is enough for your students to do any challenge? Why computer has to come? Well, I go to the next point. The second point is safe design. Safe design. If you remember, when we teach either design 1, design 2 teachers, there may be many design teachers, I presume. I don't know whether I should pull Shibu into it. If Shibu is around. Shibu, can you hear me, boy? Shibu is from Engineering Design, Anna University.
Yes, sir. He is responding through chat box, sir.
Okay.
I
He's
think
a design teacher. He's a design teacher. Okay. And the design teacher will be teaching them design automation elements. Let's say connecting rod, crankshaft, whatever the design, anything. The last line in the design submission, when he's doing a project work or when he's doing an assignment, what is the last line, Shibu? Put your response in your chat box itself. Murugan will read it for me. What is the last line in the chat box? Last line in the assignment or in the test or in the project of a design. Murugan, can you read what Shibu has put? For that matter, anybody can put, yeah. Murugan, do you get any response in the chat box?
yes, sir. Yes, sir.
What
It
is
is
it?
safe, like that. You know.
Okay.
Sir.
Okay. The last line, Shibu will give mark only if he writes at the last line. Therefore, the design is safe. That sentence must be there. Then only the assignment is S grade. Now, for him to write that statement at the end, therefore, the previous line must justify that. So the previous line, he'll say, the stress developed is within the allowable stress. Therefore, the design is safe. So you are measuring with two stress. One is stress developed or stress induced, and you are comparing it with the stress allowable. What is the allowable stress? If the stress developed is within the allowable stress, then you will say this design is safe. If the stress developed is not within the allowable stress, then the design is unsafe. You don't want to do the design. So you have to do something else. You have to modify the design. So simple job. You are now designing, let's say, a connecting rod. And the stress developed in the connecting rod is more than the allowable stress. Allowable stress comes from the material. Okay. So you now have the allowable stress. Allowable stress, the yield stress by the factor of safety. So in case if it is not safe, what do? One simple straight change the material. In some aluminum, you make it into steel because the allowable stress of steel is high. Therefore, the stress developed is within the allowable stress. Simple. If not, if the material already selected is steel, what do? Change the dimension. Change the diameter, change the wall thickness. Okay. So we want to make the design as safe design so that it will not be rejected, it will not be returned back. But today when you have students who go with your design 1 and design 2 knowledge where they know how to do a safe design, Okay. But the industry today, Tata Motor Company, they say it's not enough if you make a safe design. What design you have to make? They say the number 3, optimum design. So they have put a new word, optimum design. And if you go to MNC, Ford Motor Company, they will say robust design. In case if we are stopping with the safe design only, all right, you are a design engineer, but then you are not a competitive design engineer. If your student has to be competitive, the Tata Motor Company says, can you make an optimum design, man? The stress must be within the allowable limit, but it must less in weight. Oh, my dear. So I gave you a safe design, man, put this dimension. No, Bhaiya, I want the material to be reduced. So I want optimum in weight and optimum in size. I can't have such a big component there, no space there. No space there. Optimum in size, optimum in shape, optimum in cost, end of the game. So now don't just stop with safe design, go with optimum design. Okay. Then comes robust design. What is robustness? Okay, your design can withstand, but then can it withstand if it is elevated temperature? Can it withstand if the truck is going in desert? You have designed it for Ashok Leyland, you have designed a truck for you to drive it on the road. Can it drive it on the road in Rajasthan desert? Can it drive it on the road in Himachal Pradesh where it is cold, minus? It must be robust enough. Anywhere, everywhere. All-terrain vehicle, all-weather vehicle. So now they are looking for robust design. Now, there was a time when we are depending upon the material, steel or aluminum as the component or as the candidate. But today, now aluminum, for your kind information, by the year 2030 to 35, 10 more years maximum, okay, there will not be any aluminum at all in the whole world, man. You hear me? In 10 years' time, aluminum will not be there in the whole world. They have taken stock of the amount of aluminum ore in the Mother Earth, and then they have taken every year how much aluminum we are consuming. We are consuming a lot of aluminum for aircraft structures. We are consuming a lot of aluminum for the automobile structure because it is less weight, good strength, no corrosion. But now, aluminum is not available to you in 10 years' time. So what will you do? What will you do? So they went for new material. That is how the composite came. Some of you are working on composite, you will know why composite. Composite can replace the metal with a higher strength, lesser weight. Now, your robust design must be account for any new material, anything new which is coming up. Okay? Some of you work on composite will know what is the fiber reinforced material. So the fiber strength is varying. How you are laying the fiber, the direction in which you want more strength, put more fiber. Things like that. Your design must be a robust design, accommodating anything new happening. So now, your students who were trained in safe design, they can do the job with the design 1 and design 2 knowledge. But if you are going to think of optimization, your safe design theory which you teach may not be enough. If you're going to think of design, the new thing that is coming up is not enough. Everybody is looking for lightweight, more strength, less cost. How is it, boy? Lightweight, strength, cost. Your design engineers are now challenged there. They need help. They need help. FEA is a good help. Okay, that's the first message I want to do. that FEM can be your helper, number one. Okay. My next slide says, okay, it's a silly simple example. It's after all cantilever beam with the UDL and with the pointer load at the end. And you know pretty well that the maximum stress is developed at the fixed end, because that is where the maximum bending moment is going to be. Okay. The next drawing is a diagram, and you'll know pretty well, due to both concentrated load and your distributed load, you have a maximum bending moment at the end, and then you are going to calculate the stress developed for that maximum bending moment, so that where the bending moment is maximum, there the stress is maximum. So now that is the maximum stress that is going to be developed, and you must design your cantilever beam, which can have a hollow circular tube, which can be head section or rectangular section, whatever it may be. You could see the various sections. All right, fine. So you are redesigning. Now, question. Okay, I have selected a tubular circular member as the cross section to withstand and the pointer load. Very good. So I calculate the maximum bending moment. I have given here maximum bending moment is P into L for the constant load plus WL square by 2 for the UDL. That's the total bending moment. And is equal to F by Y is equal to E by R. So F is the bending stress. So that's equal to M by I into Y. So what is that? F max. F max is maximum where there is M max. Very good. So now what is I? Moment of inertia. Moment of inertia is the criteria for your reducing the stress. Moment of inertia is more, then the stress is less. So I can look at the section. Is it I section? Is it less in moment of inertia? Or is it the rectangular section? High in moment of inertia? Okay. So you check up and then choose that section. You found out what should be the section dimension, outer diameter, inner diameter, wall thickness, everything. Now, look at the bending moment diagram. Look at the bending moment diagram. Okay. Moment is the fixed end. And you have checked what is the maximum bending stress, and you have identified cross section that is able to meet the requirement. Now, at L by 2, at the midpoint, what is the bending moment? Bending moment is less. Can you see the bending moment diagram? But if the section with a hollow circular pipe with outer diameter, inner diameter, wall thickness can meet maximum bending moment, it can obviously meet the midpoint L by 2, where the bending moment is less. Design is same. At L by 4, bending moment is very small. So design is safe. Question. Then why should you have the same section there? All right, you selected the section, calculating the maximum bending moment of the fixed end. You calculated the outer diameter, inner diameter, and wall thickness, and you designed this, and they can only meet the requirement everywhere. Question. Isn't it a waste if it is the same section throughout? It's going to be heavy. I don't need it. Your mind is thinking. Now I know bending moment variation. And the maximum bending moment is at the fixed end, for which I have designed a rectangular section of B and D. If that be the case, when there is L2, I don't need to have the section B and D. I can have B and D by 2 after. If it is going to be at L by 4, I don't need the same moment. B into small d. It may be 1/10. So now I have my section not having B and D constant, but the depth is varying. B into D or B into D2, B into D. I'm just keeping B as a constant one. D only is varying. Can you see amount of inertia I is BD cubed by 12, 1 by 12 BD cubed. So as D is decreasing, decreasing, is cubic time I is decreasing. Can you see the stress variation is tremendous cubic curve. So the bending moment diagram is vertical and the bending stress curve is a cubic curve. And your new design can now be in the sections which are reducing the depth cubic order. Now do you have a good understanding of what is optimum design? Okay, optimum design, you selected the maximum geometry, design geometry, and then you are trying to optimize it, smaller in shape, smaller in size, smaller in weight, smaller in cost, and bring a new design. If there is a manufacturing gentleman here, he may ask, sir, I agree your mathematics, but where will you make a rectangular varying section like this, sir? A cantilever beam, which is varying rectangular. I shoot back the answer to the manufacturing man. You have the manufacturing process. You have a manufacturing process. You're not going to have a constant cross-section manufactured. You're going to have a variable cross-section. You may say it may be costly. It's all right. Now you are producing everything mass production. So instead of having million numbers of constant cross-section cantilever beam, you have a million numbers of varying cross-section beam. Then your saving is tremendous. So now I have taught you with a silly simple example what is an optimum design. Today industries, everybody is competing with one another to say that our design is a optimum design, our cost is the lowest cost. Now guys, just you are going to go for a new car for you. You are going to buy a new car. Okay. So you are looking at the model which are released. Last week there was a there was a new model of Nissan. Okay. The old model is there and the new model is there. Okay. What do you look at? What are the new features? You look your new car to have a new features. You like it. And you look, the new car is having a ride comfort. Vibration level is reduced. You see, the new car is giving a better mileage. For 1 liter petrol, how many kilometers I can travel? You like everything. Then at the end, there is a price also. If the price is going to be double the previous car, I don't want this. You expect the price to be less than the previous model, isn't it? So a fellow, your student who joined Nissan, he is going to design a product which is going to be safe in design, optimum in design, lesser in cost, more time, long life, etc., etc. He needs help. Your student needs help. Yes, your design 1 and design 2 cannot carry all these things. But then, as he is demanded in the industry, if not, you have to go and do a welding shop only. But for you to become a competitive design engineer with the leading MNCs in this country, your student needs help. Please help him. One good help is to teach him what is the new tool called FEA. Okay. All right. Now, those of you who attended my class, you may remember that we go with the known knowledge. All of us have gone through the strength of material in 3rd semester and 4th semester. The first lesson in strength of material is a bar stability and axial load. Okay. So the maximum displacement at the free end the maximum displacement is equal to PL by AE, a rod of length L subject to a constant load P at the end, having a constant cross section, and the material property E is Young's modulus. Therefore, the maximum displacement, so much. Then you work out the maximum stress and you check for your design. Okay. Now, if I'm going to, okay, this formula you may remember, U max is PL by AE. How did you get it? You got it when the rod take a small section, length dx, and it is having stress by strain is equal to Young's modulus. So stress is E into epsilon, strain. Strain is change in length by original length, du by dx. Therefore, the expansion or the elongation of the small segment is pdx by AE. Okay. Now you integrate it from 0 to L, integral pdx by AE. When you integrate dx, it becomes x, so it's px by AE. At x equal to 0, it is 0 displacement. At x equal to L, the maximum displacement, that's equal to PL by AE. This is how the Simpson teacher derived to you. Okay. And if I'm going to show you graphically that a cantilever beam will be elongating, you could see the red line. And I have demonstrated it that it is going to vary linearly. At x equal to 0, it is 0. At x equal to L, it is PL by AE. At x equal to L by 2, PL by 2 AE. X equal to L by 3, PL by 3 AE is PX by AE. Where do you want x? Substitute x, and it is a linear variation. Okay. This is the simplest, straightforward centennial first day class. Okay. Now, generally, teachers will have a liking to modify. What do? Okay, if the member is a taper member, not a constant cross-section member. So, how the displacement is going to vary? Okay. So, A is no more constant. It is a function of x. So, if you are going to look at the variation of the displacement, integral 0 to L, P dx by A is no more constant, A of x. So, when you are going to integrate, P and E can be taken out, integral dx by AX. So, integral dx by AX, your student will know because he has studied integration in semester 3. He will say integral dx by AX is log AX. So, put the limit 0 to L at x equal to 0, it is 0. At x equal to L, it is maximum. But the variation is going to be logarithmic. The variation is going to be logarithmic. If it was a straight rod, the variation was linear. But when we make it to be a taper bar, it becomes logarithmic. Now, I'll put some more salt. A taper bar, subject to a constant load P. Now, at the end, in small letters, include sulfate also. Include sulfate also. Because that's what engineering is. So the sulfate is acting at the cross section and it is varying load because sulfate is volume above multiplied by density. So volume is a function of x. Therefore, we are going to have the variation as a function of x. So if I'm going to put the mathematical equation, integral p bar of x dx by a of x. What is p bar? P bar, there are two loads now. One is axial load P, constantly acting, and sulfate. It varies at any section x. So you are now having an integration. Look at it. Integral px dx by a of x. When it was just a straight rod, I'll go back. Okay, a straight rod, integral p dx by a. So integral dx is x, so it became linear. When it was a taper cross section, okay, we included the taper as a function of x. So it becomes integral dx by a of x. So you set the variation as log x. Linear variation became a logarithmic variation. Now we added sulfide. When we added sulfide, your numerator load is no more constant, it's a function of x. And the area denominator is no more constant, it's a function of x. So you have an integral, numerator is a function of x, denominator is a function of x. You have formula, integral dx by a of x, the formula is log x. Now integral p bar x dx by a of x. Numerator is a function of x, denominator is a function of x. What is the formula? Oh my dear, the integration book doesn't give you a formula. If the numerator and denominator are functions of x, you don't have an explicit formula. There may be condition, they will say, if the numerator is the derivative of your denominator, there's some formula, but it depends upon. Or what will you do? You will split it. You will say integral ax by denominator plus b by denominator. So you have to factorize a and b. But it may not be possible always to factorize. So to bring the story short, you got stuck with the integration of a bar which is tapered, including the sulfate. You have a situation, there is no integration formula is available to you. What do we do? What do we do? In mathematics, when we don't have an integration formula, math doesn't give up. Math doesn't give up. At least I had idea, yes, integration formula is not available. But from the knowledge which I got, if it has a constant cross-section, it was linear. Taper cross-section, it is logarithmic. Now it is taper cross-section, includes sulfate also. So it is going to be something, linear became a complex logarithmic. A complex logarithmic will become complex logarithmic. Oh. That means there is no explicit formula. It's complex formula. Okay. So what mathematics taught in the fourth semester, our students after studying integration third sum, fourth semester they go to numerical method. Numerical method. They teach about trapezoid method, Simpson's method and all. What are they? What are they? They are approximations. Now the curve which I have shown between 0 to L is a function of x, f of x. That's what we are trying to integrate. No explicit formula. Okay, divide the curve into 10 segments and join them by a straight line. So each one is a trapezoid. What is the area of trapezoid? There are two parallel sides with a distance between them as h. So f1 plus f2 by 2 into del h. There are 10 numbers of trapezoid. Add all the areas of trapezoid. So you get the area under the curve is sum of your trapezoids. That's what the numerical method taught, trapezoid method. And also they taught instantly that yes, the curve is some complex order, complex logarithmic. I don't know what is that. I simply made a trapezoid by joining them by a straight line. So I caused error. There is error. And total error is also increasing. Okay. But then you are an engineer. You are thankful to your mathematician. All right, I don't have an exact answer, Baba, but I have an approximate answer. Be happy. Be happy. Mathematics didn't give you an exact answer, but mathematics given you an approximate answer. If I divide it into 10 segments, you divide it into 20 segments. So your delta H becomes, in the previous case, 0.1 L, 10 segment, 1 by 10, L by 10, 0.1 L. Now 20 segments, L by 20, point OHL. All right. So now what happened? Error is still there because it is trapezoid, linear, but the error is small. If I'm going to have 100 segments, error is there, but error is small. Error is small. I have 1,000 segments. Error is small, but error will be there. It is not exact solution, but I'm going towards exact solution. It's all right. I don't mind that. I don't mind that. Because in the absence of an exact solution, formula is not available in the math book, but math book gave me a formula for approximate solution by trapezoid. And math book also told me you can refine your error by increasing the number of segments. Okay, good, very good. I'm glad as an engineer. But it's still approximate, you will never get exact solution. So the numerical method class, in the next class, they taught another method called Simpson's method. What is Simpson's method? Instead of joining by a straight line and make it into a trapezium, you join them by a quadratic curve. Join them by a quadratic curve. So what's happening? Error is reduced. Oh, good. So therefore, quadratic method or Simpson's method is better than linear method or the trapezoidal method. Okay. So that means I'm glad about Simpson's method. All right. Even in Simpson's method, I have 10 segments. But if I make it 20 segments, error is still small. Error is still small. But do you get exact solution? No. Never you will get exact solution. But you will get still better improvement. Then someone else, after all, mathematicians, okay, you have trapezoidal method, there is linear, and you have quadratic method, there is Simpson. It's better. Now have cubic variation, man. You have 10 segments and connect them by a cubic curve. Yes, solution is still better because what is after all the exact solution was highly, highly complex logarithmic. What is the log curve? Log x equal to 1 minus 1 by factorial 1 plus 1 by factorial 2 minus 1 by factorial 3 plus 1 by factorial 4 up till 1 by factorial n. It's a series, nth order series. Instead of that, you approximated only the first term, linear, that is trapezoid. You added second term, quadratic, Simpson. You add third term, cubic. So you are improving your solution. You can have fourth order. Actually, your curve is an nth order curve. But you cannot find n tending to infinity. So you go linear, quadratic. Another solution gave you, instead of dividing 10 segments, divided 20 segments, better solution. Instead of 20 segments, you divide 50 segments, divide 100 segments. So both routes, either you could increase your number of segments or you could increase the order of approximation. You will get an improved approximation, but never you will get exact solution. Never you will get exact solution. Now you are an engineer. You have to make up your mind. In the absence of an exact solution, I don't mind an approximation, but I like to have a better approximation. Two routes, either divide number of segments more, fetch to be smaller and smaller and smaller, or increase the order of approximation from linear to quadratic, quadratic to cubic. If I ask a question, which is going to give you a better solution? It's by increasing the number of segments are you going to get a better solution? Or by increasing the approximate order you are going to get a better approximation? To tell you the truth, I don't know. I sincerely don't know which is going to give me better solution. But I know one thing. Both gives me solution and approximate solution. Both gives me a solution which can be improved upon by increasing the number of segments or by increasing the order of approximation. I conclude this session before you break with one sentence. Finite element method is an approximate method combining both the H refinement and P refinement. By refining the H, reducing and reducing and reducing. By refining the P, increasing the order of polynomial. Finite element method is both H refinement and P refinement. And that is one of the reasons why finite element became a best approximation. Best approximation. I don't know whether I have impressed you enough. I impressed you enough. You are a design engineer. You are in the wilderness. You are in the wilderness. You don't have a solution because things are becoming complex and complex and complex. Nobody likes to have say your office table is having 4 legs, right? And your dining table is having 4 legs, right? And your living room showcase table is also having 4 legs. The office table is 4 straight legs, constant cross section. I don't want to pull Malakali again, but the ladies here will say, would any of the ladies like to have your dining room table to be a straight office table like? They don't like. If I ask, yeah, if I ask them, they say, the next door lady has got a table, 4 legs, tapered, and the tabletop is a oval shape. Looks so gorgeous. I must have one like that. So what is she looking for? You are a Santhamadi man, you may say, a straight leg is very sturdy, strong. But the lady is looking for an inclined leg with the oval top. Now that is good to look at. That's design. That's design. That design is called, oh, I am not able to see you. That design is called aesthetic design. Have you heard the word aesthetic design? It is not enough if you make your design to be safe. Not enough if you make a design to be optimum. Not enough if you make a design to be robust. Can you make aesthetic design pleasing to look? Then your wife will love it. Otherwise, she'll always grumble, what a dining table you bought. You may say, oh my God, this is very strong, sturdy, Santhamadi proves. Go with your Santhamadi. Human being looks for something better to look at, aesthetic. Now, your student tomorrow, when he is going to design a table, okay, he is going to go to, say, Raipata. He is going to get an employment. If you are going to design your office table, you'll be paid maybe 15,000 rupees. But if you're going to make an aesthetic design with your dining table, you'll be paid 25,000. But then, if you're going to look at your center table, the center table will have 4 legs. It is neither constant cross-section nor taper cross-section. It will look like the trunk of the elephant because the table is looking like an elephant. The 4 corners will look like an elephant with the inlaid work of the ear of the elephant and with the trunk of the elephant. Now that table attracts not a housewife, but a tourist who comes to this land. Because he never seen elephant in his life. He has seen only in the picture. When he came to India, he went to Mudumalai Hills and he saw elephant and elephants because Tourism Development Corporation knows the weakness of the guest, the tourist. So he'll take them to a inner Mudumalai where you will see the herd of elephants, mummy elephant, daddy elephant, baby elephant. Now recently I was told that they have arranged an elephant safari where the tourists can climb onto the elephant and he will be taken to the interior of the forest for some distance and brought back. And he is so delighted. He not only saw an elephant, he saw a herd of elephant, and he ride on the elephant. Time to go back to his home country. He can't carry the elephant with him. He wants to have the memory of that. So he comes to Raipeta's showroom, and the fellow, knowing the weakness of our client, he's not going to show you a strong office table. He's not going to show the beautiful dining table, but he's going to show the centerpiece table, which has got 4 legs. It's neither constant cross section nor taper cross section, but the section is varying. How does it vary? Like a trunk of the elephant. Can somebody give me what is the equation for the trunk of the elephant? Tumbikai. யானை தும்பிக்கைக்கு என்ன equation போடலாம் சார்? Put that equation and do the integration. You can't find a formula. So you have to go in for your approximate method. Your trapezoidal method is an approximate method, but it's linear. Your Simpson is an approximate method, which is quadratic. In reality, it is nth order. So now what do? Increase the number of elements. That's what FEA means. Increase the order of the element, linear element, quadratic element. We'll talk more about it in the 1-week course now. I'll stop at this stage. We'll have a break. We agreed that I'll have a break for about 5 to 10 minutes. Then you'll come back. I'll take a bit more of mathematics to introduce you to what is finite element method. Over to you, Murugan.
Yes, sir. Thank you, sir. Dear participants, we will have a 5 minutes break. Then we will resume the same session through same link, participants.
Break. Yeah. Okay.
லஞ்சுக்கு வரேன்னா வருவா. சும்மா போன் பண்ண இரிட்டேஷன் ஆகும். Not bothered.
Yes, sir. We
Sir,
can start.
audible,
Can hear
sir. Audible, sir.
Audible.
Can any of them be able to hear me?
Sir, audible, sir. Sir,
Can you hear me, guys?
your voice is clear, sir.
Mulakudi, can you hear me, ma?
Yes, sir. Yes, sir. I can hear you, sir. Yes, sir. I can hear you, sir. Sir.
Can you hear me?
Yes, sir.
Okay, I realized it. I didn't put my earplug in. என் இயர்போன் போடலன்றதுதான் கூப்பிட்டீங்க.
ஆமா சார், இயர்போன் மாட்டாதான்